Hello again. Sorry for the inconvenience. Yeah, actually, my Mac didn't want to share stuff. The last time, can you see my screen?
Yes.
Yes.
Okay, perfect. Um, the last time I promised you that this one slide of the multi-harmonic ansatz was wrong or didn't show the whole story. I think it was slide 10 something. Okay, yeah, slide 12. Here we had the results in the following equation, and the equation started and ended somewhere off slide. So I put the equation in one slide and I uploaded into the Teach Center, into the course. Here you have the section magnetic heat coupling, and there is a slide multi-harmonic missing part. Is it okay for everyone?
Yes, perfect.
Okay, perfect. I noticed that I didn't plug in.
Yep, probably yes. Before we start, we do a short recap of the last week. Do you have any questions in specific, or should we go over the slides and discuss some stuff? So probably I will select some of you and they will explain it a little bit. Then I will start from the top. Probably Alexander Siegel can explain a little bit on the heat conduction equation and how we arrived at it, and what's the background. Just
Okay.
put in your own words.
I will try my best.
If you kind of miss some words, I will help you out.
Okay. Can we go back 1 or 2 slides, please?
So Alex, are you here?
Yeah. Can you hear me? Can you hear me?
I can hear you.
Can you hear me, Stefan?
Yeah, I can hear you.
Okay. So it's
Okay.
working now.
So I show the slides and you just explain a little bit.
Okay, I try my best. This was very, very, very new for me last time, and I didn't really have time to recap it for myself. So
Yeah. No worries.
Oh, okay. Thank you.
We'll get through it. Okay. Topic was heat conduction equation. Do you know how we came up with it?
Yeah, it was like so how the heat is changing over time and area or within the volume, and we have I think these are these parameters Cp and lambda are the parameters from the material. So
Okay.
They slightly depend on temperature, but they are.
Okay, excellent.
And then I think we bring in the power QH, right, into the volume.
Exactly, and we apply the power loss. So the two losses are enter here at the QH, and that's how we couple the stuff.
So this is derived from the eddy current, right?
Yeah, exactly.
Okay.
Then I will thank you very much. Anyone of the others would like to explain a little bit what the eddy currents are. Probably I just select the next one, Anis. As probably an idea. I will put up the slides with the eddy currents for you to make it a little bit easier. I think it was this slide.
Okay. Yeah. So essentially, due to the magnetic field that is present, current starts flowing in some parts of the conductor, which are mostly located on the outer regions of the conductor, and this is also called the skin effect, where the current is flowing in these outer parts of the of the conductor, and this is happening with the only when we consider time changing magnetic fields. So yeah.
Okay. Yeah. So to sum up, so eddy currents arise when we have an alternating input, so like voltage or the current itself, and then in a conductor the flow is flowing in the outer part, and this is related to the skin effect, or is the skin effect, and yeah, that's basically what's arriving when we have alternating currents and yeah, conducting and material. Okay, excellent. What did we have left? So I don't know who hides behind Kinder. Probably he could explain a little bit on the nonlinearity of the material parameters.
The material parameters.
I will put up a slide. Yeah.
Okay.
Probably we just do the commutation curve, and
the commutation curve shows us how the magnetic current depends on the magnetic field.
so
And it's a hysteresis. That means if we walk through it, there will be energy lost in the material.
okay, and this lost energy is then transformed into heat.
Into heat, yes.
Okay.
I think.
Okay, these are the commutation losses.
Accommodation losses, yes.
I guess they are different from the losses due to the eddy current.
Yes, because the eddy currents losses depend on the resistor of the material in which it is transported, and the losses in this of the hysteresis depends on the field vector of the magnetic field, which changes in its direction.
Okay, so
and therefore makes these losses in the material.
Okay. I personally have no idea how they are how much is lost due to commutation and how much is lost due to eddy currents. But probably you can ask Klaus in the exercises if he has any idea how much contribution we have from the commutation losses and how much from the eddy current losses.
Yes.
Would be probably interesting when you consider iron or some magnetic material.
And
okay.
If the material is magnetic hard, it is it's wider. The curve would be wider, and
Okay, so this curve would be
So
like
there
this.
would be more energy lost if we
Okay.
walk through the curve.
Mm-hmm. Okay.
Okay.
Very nice. Thank you. Next, we will try that Lucas explains. Oh, I'm hearing a very loud echo.
Okay. Is it coming from me? Yeah. Okay.
I think so. Then probably Lucas doesn't explain today. Probably we go on with Tobias. Can you explain us a little bit about what's the idea behind the multi-harmonic and why don't we just go for a harmonic computation?
Yes, of course.
I
First,
will put on the multi-harmonic slide. Yeah, probably this one. Yeah.
yeah. So the basic ideas, the basic idea of a multi-harmonic ansatz is that you can firstly decompose the vector potential in case you have somehow a periodic excitation signal of the problem. For example, imagine a simple coil and and you excite this coil with a harmonic current. Then you will also achieve a quite harmonic magnetic field. But as we know, if we have ion material in our problem domain, the nonlinearities introduced by the pH curve, which we saw on the previous slide, or the slide which the previous color, this combination curve.
This one.
And if you jump one or two slides forward to the sinusoidal shaped signal, to this, you can see that we don't achieve a sinusoidal flux density, and this is caused by the non-linearities of the ion material. So we have already seen the PDE in time domain. And the problem is that this can be quite, numerically quite an effort to solve due to the nonlinearity. And as we have seen in, I don't know when we had this lecture, when we discussed the Newton method, you need special numeric techniques for deriving a sufficient approximation, or that you have to apply somehow an approximation, and this non-linear algorithm might take several hundreds of iterations.
Yeah.
And you therefore might raise the idea to also decompose the relativity into a harmonic series. You can see this at the bottom of the slide. And if you can decompose the relativity in this way, you can set up or you modify the actual PDE to at least in frequency domain to a linear PDE, and you then doesn't mean you can reduce the necessary number of of iterations to solve the non-linear equation system arising from the non-linear relativity.
Mm-hmm. Yeah. So that's basically it. We transform the nonlinear system in a set of equations of linear systems and kind of truncate the series. That's the multi-harmonic ansatz. So in terms of effort, we get rid of the iterations, but on the other side, we get a much bigger matrix system. So this is kind of a trade-off that you involve with this method, and just keep it in mind. On the one side, in the nonlinear system, you do the iterations. On the other side, for the multi-harmonic ansatz, your matrix system will get larger.
So you don't need any iterations for the multi-harmonic ansatz, because on the next slide, or if you go one slide forward in the presentation, you at least the lower part looks for me that you still need somehow an iteration in the solver algorithm.
Yeah, iterations in a different sense. So it's not really a following a curve in the time domain. So it's a little bit different.
Yes, of course. Thank you.
Yeah, but indeed you need iterations, but on the other side you don't have this really kind of stepping algorithm. Yeah, that's true. So okay, there was one additional point I would like to point out. Yeah, but I missed this point. So anyway, yeah, and of course you also need iterations to solve the matrix system itself. So if the system gets very large, there are iterative solver to solve the inverse of the matrix system itself. Just keep that in mind. If you have very large linear systems, there are also iterative solvers that solve the system itself. That was the second point. Okay. Any questions on last week's theory? I think we did a very nice recap, and thanks all the contributors. And we will start again with the skin effect. So the conclusion is that the overall alternating current in a wire can just flow in the outer part of the cross section. Just keep that in mind. And deriving the distribution of the eddy current, we start with the equation here. We then take the curl of this equation. Then we arrive at this equation of the flux density, and then inserting the second Maxwell's equation and Ohm's law, then we arrive at this equation there. And this equation describes how the eddy currents are distributed within a bulk material, a conductive bulk material. Going one step further, and if we have a convex domain and we say, okay, the divergence of the field is 0, then we can replace the more complicated curl-curl operator, which you see here, by this simple vector analysis identity, and then we end up at being this divergence being 0, and that we have here a vector Laplacian operator, and the result is this simple equation. We have the Laplacian of this capital P is equal to the right hand side. Here should be a vector quantity. Sorry for that, it's misplaced here in the scalar notation. If we now is having this equation, so that's basically it from the theory, having this equation and assuming a semi-infinite half plane in the x direction. So we have here a surface, and this is bulk material. This bulk material has a conductivity and has a mu. And then we do an ansatz for the flux density here in y direction, and doing the Fourier transform of it. So here's a complex ansatz for that, and if we insert that complex ansatz into this equation up there, we end up at this equation, so that the magnetic flux density in decaying or changing in the x direction. So the x direction is down here into the bulk material. That's also the stuff we would like to derive. How the flux density decays, going away from the surface of the material, and this is somehow related to the temporal change of this flux density. And here we have the equation or the relations. Here then we can do some definition of the parameters of this equation, and we obtain the skin depth delta here as just a simple definition with regarding the parameters here, and that's basically it from the setting of the equation. So keep in mind this equation up here, and that's an equation which can express a boundary layer. Boundary layer is probably more familiar in the context of fluid dynamics, but here we have also kind of a boundary layer equation, but it's a little bit different. Compared to fluid dynamics, we have now here a complex boundary value problem, and this is treated a little bit different. Okay, then we could do a physical solution as an ansatz, as we did it here, and then say, okay, on the surface we have a value of a flux density which is B null, and using this we can obtain then the equation of the flux density which is decaying. And regarding the definition of the current in the x direction, we can derive now how the current decays with depth. So this means probably my cursor is fixed. If we have here the z direction, and we would plot the current in x direction, so just then this is the decaying term, so the current will somehow decay. Oops. And it would look like this somehow. It's an exponential damping or decaying of the amplitude, and at z being the penetration depth, we have this value, more or less, of the of the current, and yeah, that's how the current decays in the z direction. And this corresponds, as I said before, to a boundary layer problem, and thus it needs a special care during meshing. To the audience, what do you think will we need for meshing the boundary value problem? Do you have any idea? So probably I'm just pointing out someone. We start from the top again. Alexander Siegel, do you have any idea what it could imply for the meshing?
Yeah, in the region where you expect the eddy currents and the penetration depth, of course you have to mesh finer. So I think Klaus told us a rule of thumb. So if you have a penetration depth of 1 millimeter, you should resolve this in so one element should be 0.25 millimeters, so a fourth of the penetration depth.
Okay, yeah, yeah, that's true. So the general rule says, so there is in mechanical engineering a general rule. If you have, I just draw here the nabla operator. If you have high gradients, then as an engineer you conclude you need a lot of elements.
Yeah, makes sense.
Probably doesn't work everywhere. Often there is also a relation. If you have high gradients, you need high number of elements and a high order. Could also be true, but that's just a rule of thumb I would like to provide you. If the gradients are high, yeah, you probably have to resolve it. Okay.
So in the area where you expect eddy currents, you have to mesh finer.
Yeah, exactly. And that's what we are going to see in the next slides. So here just some basic background on a boundary layer problem. That this equation is the solution of a boundary value problem. Here we have a boundary value problem which is known from fluid dynamics. So yeah, if you any one of you has a little bit of background on fluid dynamics, or is it clear for you what could it be having a boundary layer in fluid dynamics, or should I explain it here?
Please explain it.
Okay, so imagine flow always flows from left to the right. That's a fundamental law of, I don't know who did it, but it's always the case. Here I'm now drawing a wall, and typically if you have a Newtonian fluid, which means if you have a fluid that is sticking to a surface, then you have shear forces in it, and if you have shear forces, then you have, then you get a flow profile which is looking like this. So here, this means that we have here kind of the value is 0, and here we have the velocity of the approach, which is called typically u infinity, and the boundary layer of the flow example then approaches from a value of 0 to the u infinity. And this is a typical shape of a boundary layer from a flow problem, and it can be described by this simple equation. Actually, it's a little bit more complicated than here the simple equation, but this equation can represent the boundary layer. And in our case, we have the time harmonic eddy current approximation, and here this boundary value parameter is now complex, and therefore we have in electrodynamics a complex variant of the boundary layer problem, which we also have in fluid dynamics. Did you understand how it is probably, or it is related to fluid dynamics, and that the shape could be similar? Okay, I take this as a yes. Here in the equation, here we have an exponential increase or decay. So here we would in fluid dynamics not end up at the U infinity, but I will show you in the next lectures in aeroacoustics that we indeed have different functions which provide the solutions for a typical channel flow in fluid dynamics and stuff like this. So it's working, and that's how we define the boundary layer in fluid dynamics, and also can define it for the eddy current problem which we have here. So as Alexander said before, we have to resolve the gradients by elements, and that's what we now are investigating. And we are looking at the convergence rates. So a horrible slide for the students. What's your impression on the slide? Probably I will select Anis. Do you have any clue what's the content of the slide?
I would have to read it a bit.
Okay. Basically, I will just point it out in a few seconds. What is happening? So if we have an eddy current boundary layer problem and we would just do H refinement, the error decays, but the method is actually not working robust. So H refinement is not the way we go. So if we do it quasi-uniform, do you have an idea what this means?
Sorry, you're asking me, or?
Yeah. Do you know what's quasi-uniform?
So maybe in some parts, so it is not everywhere the same.
Okay, quasi-uniform is if we consider here I draw a line, and I cut the line by 2 kind of, let's say, nodes. If we do it quasi-uniform, it would mean that's more or less the structure is that we're always halving our elements. So could be looking like this. That kind of the treatment of refinement is uniform, or could be quadratic or stuff like that. So that we don't discretize the exponential shape with an H refinement. Okay, did you get the message what's quasi-uniform? If you have a cell which is long H, then a next refinement step would be H half. Then the next refinement step would be H divided by 4. The next refinement step would be H divided by 8. So this kind of convergence, or if we reduce our elements like this is not robust. So probably we take the next one. Kinder, do you have any idea what's an exponential H refinement?
Exponential refinement.
Okay.
Schwer.
Okay. Again.
It will be not done in the linear way, but in an exponential way. But
Yeah.
what it means really, I don't know.
Yeah. Okay. You just imagine you have on an exponential scale or on a if we transform a length into by the logarithm, you can do then also an quasi-uniform refinement, but it means more or less all the elements or the refinement is done like this. If we say here we have on this part where I'm now clicking, I think you see it. On this side there are the eddy currents, and it means that we have refinement according to the function of the function of the solution. So the solution function is something like an exponential, and the idea is that we refine the exponential solution property, and then we obtain an order of convergence, being h again. So this is okay, but it's not also not working very well. It is also okay to do p refinement. Do you have an idea what's p refinement? So p refinement means that we increase the polynomial order of the basis of the finite element. So p means 1, we do linear elements, p is equal to 2, we do quadratic elements, and so on and so forth. We obtain good convergence rates with the p convergence, but nevertheless, it's also not working so well. The optimal way would be if we do HP refinement, which means we refine both in halving the elements and increase the order of the elements. This works very well for this type of problems. So for boundary value problems, this would be very good. This was now very theoretical, theoretic, and if you have any issues with boundary value problems or the skin, the eddy current or resolution, go to this slide and you're getting some basic information about what you probably missed in the discretization. But for the understanding, the slide is not so awesome. This is why we provide an example for you. The example is that we have a quasi 1D problem, and we prescribe an external magnetic field. The external magnetic field you see here, which is prescribed. Then we have a plate of a thickness of 1 millimeter. So the grayish, the dark grayish area is the plate, and we compute there the eddy current losses inside the plate, and we have on the other side, so the eddy current losses are computed by finite elements. So sorry. So the eddy current losses are on the one side computed by the finite element software OpenCFS, and on the other side we have an analytic formula for the low frequency limit. Probably you know from some other courses how to get to this low frequency limit, and we also have an analytic formula for the high frequency limit, which means that we can for low frequencies and for high frequencies we have an estimate how much the eddy current losses will be in this dark grayish colored area. what's your feeling about the problem or the example we are looking into? Everyone understood how it works?
So the pay eddy does show us the power, which is
Yeah, this shows us the eddy current losses, the power.
the losses. Okay.
Yeah, the power which are generated or lost by the eddy currents.
I see it's an product of current times E field. Okay. Yeah. Mm-hmm.
Yeah. So it's the power which is transformed from the magnetic field into the heat of the material inside this eddy current zone here. Yeah, and that's what we are evaluating. On the one side, we have the finite element stuff, where we now introduce different discretizations. So we, on the one side, we do some H refinement, and we would like to illustrate the stuff we, kind of explained here. And on the other side, we will also do some HP refinement and show the properties what will arise. Okay, then we go to the results. Okay. If we would do just one element with basis function order of 10, we have the following issue. This curve, the blue dashed line is the low frequency limit, the green dashed line is the high frequency limit, and here the red line with the fancy dots is from the finite element stuff, and it means if we are not resolving the eddy currents anymore in our solution, then unfortunately at higher frequencies the whole computation of the loss breaks down and will just stay constant. And we have here now a gap between the real losses, which will follow the green line up there, and the model losses in our finite element solution. And this is actually not nice. And this will be the case if we don't resolve the gradient fine enough, as it was pointed out by Alexander before, and that issue can arise. If we now, we did one element. If we now increase the number of elements, as I said before, we do HP refinement, and we now use 3 elements, then we see, okay, finite element goes well over the whole frequency range. Here we have, and we get a better resolution for at least 2 orders of magnitude, but just adding 2 additional layers to the resolution. And this is also quite impressive for modeling. So there is not a lot of new further unknowns introduced, but we gain a lot. That's basically it for resolving the boundary layer. Be aware of it, that it could be an issue that you under-resolve your boundary layer. And typically you should do a grid study on the boundary layer resolution in order to prove that your model, your finite element model, really resolves the stuff you would like to resolve. Okay. And of course, here are some convergence rates for the different methods we discussed before for the conversions. But yeah, that's just some nice graph if we would like to compare your own finite element solver probably to CFS. You could use this graph. Okay, that was it for the boundary layer and the resolution of the skin effect and the eddy currents. Do you have any questions on the skin effect and eddy currents and the resolution regarding finite element? Okay. If it is not the case, would you like to do a short break?
I would not mind.
Okay, so we do a short break, probably 3 minutes, and then we go on. Okay, so short break until 5:05, and yeah, we will see us in 3 minutes.